One way to view the Goodstein function is that it tells us how long a certain decreasing sequence of ordinals is. Associated to the Goodstein sequence, we had this decreasing sequence of ordinals, gamma 1n, gamma 2n, and so on. And g of n is telling us how long the sequence is, how many steps before the sequence reaches the ordinal 0. The function h alpha is also looking at a decreasing sequence of ordinals. If we calculate h alpha of n, this is equal to h alpha bracket n of n plus 1, which is h alpha bracket n plus 1 of n plus 2, and so on. And the sequence of ordinals, alpha, alpha bracket n plus 1, and so on, is also a decreasing sequence of ordinals. When we reach 0 at some n plus k, we stop and we return that value, n plus k. So h alpha of n is the number n plus k, where k is the length of this decreasing sequence of ordinals. So the way we'll compare the Goodstein function to the functions h alpha is to compare these sequences of ordinals. Basically, what we want to show is, first, for every alpha, there's an n, so that for all m greater than or equal to n, gamma m of m is at least alpha. And second, if gamma I of n is greater than or equal to alpha, then also gamma I plus 1 of n is greater than or equal to alpha bracket I. Because if we have these two claims, we'll be able to argue as follows. For any alpha, choose n big enough so that for all m greater than or equal to n, gamma m of m is greater than or equal to alpha. That's the first claim. Then gamma m plus 1 of m is greater than or equal to alpha bracket m by the second claim. And gamma m plus 2 of m is greater than or equal to alpha bracket m plus 1 by the second claim again, and so on. In particular, h alpha of m is m plus the length of the lower sequence, and g of m is m plus the length of the upper sequence. So the top sequence is at least as long as the bottom sequence, because the top sequence can't reach 0 unless the bottom one does as well. So g of m is m plus the length of the top sequence, which is greater than or equal to h alpha of m. And that means for every m greater than or equal to n, g of m is greater than or equal to h alpha of m. There's only one little problem with this plan, which is that the second claim is false. Gamma 1 of 2 is simply omega, and gamma 2 of 2 is 2. So gamma 1 of 2 is greater than or equal to the ordinal 10,000, and 10,000 bracket 1 is 10,000 minus 1, which is 9,999, which is bigger than 2. The problem is that even though 10,000 is a small ordinal in the grand scheme of things, it's merely finite after all, and we know about infinite ordinals, even though 10,000 is small, 10,000 is complicated. It's a sum of 10,000 terms, omega to the 0 plus omega to the 0 10,000 times. And omega, even though it's bigger than 10,000, is pretty simple. It's just one term. So to make this work, we need to introduce a measure of complexity of an ordinal. We'll call this tau. Tau of alpha will be a natural number, and it will be the largest number of times that we repeat a single term in the ordinal. As with a lot of these things about ordinals, there are a lot of ways you could define the complexity, and they're all pretty similar in how they work. I've chosen one that interacts especially well with our definition of Goodstein sequences. So what we'll do is modify claim 2. We'll say that if gamma I of n is greater than or equal to alpha, and if I is greater than or equal to tau of alpha, then gamma I plus 1 of n will be greater than or equal to alpha bracket I. And then we can fix our proof, because all we need to do is wait until gamma m of m is at least alpha, and m is greater than or equal to tau of alpha, and then we can finish the proof.